Today we're gonna talk a little bit about classification, and we'll see how we can perform linear classification. So last time we said that we had linear regression. So when we had a linear regression problem, we had, let's say, two features. We had feature 1 and feature 2, and we collected so many samples like so, and then we really tried to just plot these and try to predict one of them from the value of the other one. So let's say we put x1 on the x-axis and x2 on the y-axis, and the thing is we tried to put these values and scatter them like so, and then we try to find the best fit into this data, the line that would really describe this data, such that if we have an unseen sample, let's say that this is unseen, we can just project this point on the line and see the corresponding x2 value, the predicted value for this variable. So we used it for predicting one variable from the value of another variable. Of course, this could be extended for multi-variables, so we can extend this and just use many variables to predict one value and so on. But for the time being, we just talked about this one-to-one prediction problem. Okay, so today it's gonna be a little bit different. We are gonna talk about perceptron, which is the first classification model that we will talk about. So this is now used for classification. And what we were doing here, we were doing regression. And if we remember last time in linear regression, we were also using a cost function, and we had this cost function defined, and then we differentiated this cost function with respect to w to get our change, and then we differentiated this cost function with respect to our bias to get the change of our bias. And also, if you remember, we had this relationship between the weight and the cost, where we were plotting how changing the weight would change the cost, such that we can initially have our weight, let's say, at this value, and then we can update our weights, and we can just keep progressing like so with the value of the slope until we reach the point where we have delta W equals 0, meaning that we have absolutely no change because we have reached our global minima. Okay, so do you have any questions, any questions or anything that is really confusing you in the last lecture about linear regression or gradient descent?
Yeah, why do we do, what's the purpose of the regression exactly?
So you are asking about why we are doing regression, right?
Yes.
Okay, so let's say that you have a relationship between two things, okay? You noticed something interesting. You noticed that if you are collecting some data from your study hours, okay? And then you had several exams, so you have a lot of marks. You found that there is almost a linear relationship between the two. If you spend more hours, let's say if you spend 1 hour studying, you will get out of 10. Let's say that this is out of 10. If you spend 2 hours, you get 2 out of 10, okay? And so on. So you find this relationship between the two, okay? And then you don't really know. You don't really know. So this is not existing in the data. So let's say that the data stops right here, okay? So you only got 4 exams and you collected your data like so. Okay. Now you are querying about what will happen if I study for 9 hours. Okay, you find this interesting pattern between the two, that if you spend more hours, your mark is going to be higher. So you are really wondering what will happen if I just study for 9 hours. Will I get 9 out of 10 or 10 out of 10? Okay, so in this kind of problems, we are giving one variable, which is the study hours. So we put this here, and we have the marks. So we put it there, okay? And then we scatter these points. We just scatter these points. We just see the relationship between them. So this would be 1, 1, and then 2, 2, and then 3, 3, 4, 4, okay? And then what will happen with regression, this is going to use these observed data, okay, to get the weights and bias. And the weights and bias, if you recall from the last lecture, we get this like so. We can get the equation of the line using the weight and bias. So this is the weight and this is the bias, okay? Such that we can now have an equation for a line. So this equation of the line will be the best fit. So it's going to be fitting the data perfectly like so. Okay. Now that you have your data, you can just query at any point. So let's say the one that we really didn't know about 9 hours. So you can just say what will happen for 9 hours. You can just project this point on the line, okay, and see what will be the corresponding mark, okay, and this would be the predicted value, okay. And from this relationship, because it's linearly increasing with one steps, it should be 9 out of 10, okay. So we are having some observed data, and we fit a line in order to try to predict the value of this unknown variable, which is mark, from our known variable, which is hours. Okay. Okay. So what about what about classification then? So classification is slightly different. In a classification problem, we are giving some data, still some observed data, but our aim is slightly different. So with the classification problem, let's say that we have two features. Let's say that we have height, okay, and let's say we have weight. So these are the features that we are collecting from our data, okay, and we are collecting data from two classes. So that's the class. So we have a class dog and a class cat, and we are trying to differentiate between these two data sets, okay, these two classes. So the objective of a classifier is different. The classifier would take some scattered points. So let's say from one dog, from one sample, you just pick up a dog, you just pick a sample, and you just calculate the height and calculate the weight. You calculate the value of the features for this sample. And then you go to another dog and you get the height and weight of that dog, and so on. So you collect many samples from different dogs, okay? And then you collect different samples from many cats as well, okay? And then you go ahead and scatter these points, okay? So you just look at dog and you say, okay, it has high height and high weight. So if we put our data like that, so that would be the height and this would be the weight. Then the dog will have a high value for height and high value for weight. And that's almost consistent among different samples, okay? So this value will be high and the weight will be high. So the values will be scattered in these regions, right? Okay, so what about cat? Cat is almost the opposite. The weight of the cat is lower and the height of the cat is lower. Okay, so we would have the value low, so it would be in this part and in this part. So it would look like that. Okay, so Now, what is really the objective of doing this? The objective of classification. So that's our classification now. The objective of classification is to find a rule that would, using this rule, we would be able to discriminate between these two classes. So with classification, we are now, specifically linear classification, we now are trying to find this line. This line now is not fitting the data. No, it's trying to discriminate the data. So it's trying to isolate this part belonging to dog to this part belonging to cat. Okay. So that's a classification. Okay, so how to do this, we would see exactly how we are going to establish this classification. But the thing is, the main objective of doing this is also to handle unseen samples. Okay, so let's say that we have unseen sample. Let's say we enter a dark room. Okay, inside of this dark room, you know that there is an animal. Okay, so you collected data, you collected height and weight, okay, of this animal, and you know that this should be a cat. It should be a cat, okay? But now you really need to evaluate this classifier. You really need to know if this classifier is able to see your animal as a cat or not, okay? So what you do, you take this sample, let's say it's in yellow, okay? And you just put the values, the corresponding values in here, and you see, okay, it's just scattered in this part. What will happen? Then our classifier would say, basically, because this is above the line, then this is belonging to dog, right? Because
Yeah.
this is belonging to the region of the dog. So the predicted value for this will be dog from the classifier, okay? But the actual class, you know that you collected this data from a cat, then we would say that this is a misclassification.
Yeah.
Okay, so this is basically a mistake that is done by the classifier. Okay, so let's take another point. What will happen if we have unseen sample? We collected the height and weight, and this was actually a cat, and then this data is scattered. This point is scattered in this region. Then this would be a correct classification because it's belonging into this part, which is below the line, and the true label matches the predicted label because the classifier would say that this is predicted as a cat, okay, and the true label is also cat, right? So
Yeah.
this would be a correct classification. Correct classification. This is really nice because from this thing, we can really just infer some really nice insights from our data that right now we have something that we can use to evaluate our classifier, right? So we have some data, okay, that we use to come up with the rule, right? To come up with the
Yeah.
equation of the separating line. So we call this the training data, which is actually very intuitive because if we think about it, that's a training. So we are training the classifier to come up with this rule, okay? So we call this data the training set, okay? Now let's differentiate it from this unseen samples. These unseen samples, what was really the objective of using these samples? Did we use these samples to change the line, like change the weight or the bias? We didn't, right? We just projected these data and we said whether our classifier will succeed in classifying this or not, right? Is it a correct classification or a misclassification? Correct? So this is literally used to evaluate our classifier. So we call this evaluation or we call this testing set. Okay.
Mm.
So right now we can really think about differentiating these two phases. You have a training phase, you have a training phase in which you are just trying to come up with the best equation that describes how we are going to discriminate these two classes. So we call this the training phase. Okay. And during testing, we are evaluating our classifiers. So that's evaluation or testing phase. Okay. Okay. I think that's nice because right now, let's say that you have a training set looking like that. We have many samples and we have our true label. Okay. We can bring in another data set. It also have labels, but we are using this data to test our classifier. So right now, this is the training set, and the other one is the testing set. Okay. Now we are using this to see what will the classifier give. So we use this to get WMB and have our separating line. And then we use our testing data to evaluate the classifier. So the classifier will take the first point and it will give you y hat, right? Like the predicted value, okay, from the classifier. And then you can compare this y hat to the actual y, to the actual label of this sample in the testing set, okay? Now you can just convert this into something that is binary. Let's say if they are equal, you're going to just say that this is 1. If they are not equal, then that's 0. That's misclassification. So that's correct prediction or correct classification. And this is misclassification. Okay, so from this we can do something nice. Let's say that we have 100 unseen samples. Okay. Just from looking at this, we can evaluate each one of them, each single one of them. Okay. And then we can look at this and just take the average. We can count how many correct classification we are having in this data. So how many correct, okay, the number of correct classification divided by the total number of samples. Okay. And this would give us our performance measure. So you are now evaluating the performance of the classifier, and this is called accuracy. Okay, so we can use something like this to see how accurate our classifier in classifying this unseen data. Okay, so let's say if our classifier got 90 samples correct out of 100, this would be 90 over 100, and then we multiply this by 100, and this will give us 90%. Okay, so this would mean that our classifier is 90% accurate in classifying this unseen data. Okay.
Mm.
Okay, so do you have any questions in this part?
No.
Okay, perfect. So for now, we were just like just scratching the surface. We really didn't know how to come up with this line, right? We just said that if we have this line, we have two data sets, one of them for training and one of them for testing. We can evaluate the performance of this classifier using accuracy as our performance measure. Okay, performance metric. Okay. But we really didn't know how to come up with this separating line. Okay, so right now let's have a look at this and see how to do that. Okay, so for the perceptron, it doesn't have a specific, very well-defined cost function. So if you remember in linear regression, we had a specific cost function, okay? And then we differentiated the cost function. In Perceptron, it just has a weight update. So we really look at the weight update, which actually looks like what we had in linear regression, okay? And then we keep updating our weight and calculating the miss classification of samples. So the idea is very, very similar to linear regression. So what we would do, we would have our data. Let's say that we have, I'll just try to put the dimensionality of the data while doing this calculation at the same time. So this would be our weight. If you recall from last time, we had W multiplied by X, and then we had bias, and all of that will give us Y, okay, will give us the output. And then we can really name this output into something else. So instead of saying that this is Y because we were doing linear regression, so we knew that this is the Y axis, for classification, we just would name this quantity, we would name it net input, okay? And we would use the simple Z for this, okay? So now we have this variable Z equals W multiplied by X. We can say that this is W transpose X plus B. I'm just saying W transpose because if we have our weights looking like that, so it's a column vector, W transpose will just transpose this into being a row vector, just like that, okay? And it will make it easier to multiply this by our data X, okay? It will make this multiplication valid, okay? So what will happen in the perceptron is that we get our data, Z, and then what we do is that we use something called a decision, okay, a decision function. Okay, so this decision or this kind of threshold is basically doing what? This threshold is basically a very well-known function called unit step. Okay, so this unit step function is basically taking any value that is higher than 0 and saying that it should output the value 1, and any value lower than 0 would output the value -1. Okay, and then after doing that, we get our predicted class label, and then we compare this to the actual class label, and that's how we do classification. So again, let's take this like one step at a time and just think about it. Okay, so if you remember, we used our weights in linear regression and we multiplied them by X, such that we generally said we have a cost, we have an error, and we are trying to minimize this error. So our whole objective in linear regression or classification or anything is to minimize the error, is to get y hat, the predicted value, to be as close as possible to this y, to this actual value. And how to do this is by varying the value of the weight, because the value of the weight is changing the value of the z, which would change the predicted value essentially, and the value, of course, of the bias. Okay, so by changing the value of the weight and the bias, we are changing the value of the error, basically. If we look at the relationship again, we would see that changing the value of the W on the x-axis would change the cost, would change the error that we have, and we need to minimize this error. Okay, so the difference is that with classification, we have a specific label for our data. And then when we multiply the weights by x and then we subdivide, we will have a continuous variable, which is z, okay? But the thing is that the labels we know could be something binary, so it's really 0 or 1, or let's say -1 and 1, okay? So we encoded the values of cat and dog into being -1 and 1. So let's say -1 for cat, okay, and 1 for dog. So we really know that this should be like so. It should be just containing two values like that, okay? So what we can do is use this nice unit step function to do that, because this unit step function will be able to take the value of z, which is continuous, and just look at the sign of this value. Is it positive? Then it will be 1, or is it any value that is negative? Then it will be -1. Okay, and that's how we will binarize our y hat, okay, into being -1 and 1, and then we'll be able to compare it to the true class label. Okay, okay, that's conceptually what is happening with the perceptron. Okay, so let's look at the actual dimensions of our data to really try to grasp the meaning of what is happening like inside of these calculations. First of all, everything that we are doing here is linear, right? As we said, linear is just summation and multiplication, and that's exactly what we are doing here. We are not changing x into x squared or something like this. We're just adding and multiplying. Okay. So do you have any questions so far, like in the main concept of the perceptron, before going into the dimensions and seeing how it's done?
No.
Okay, good. So let's say now that this is our W transpose. Okay. So with the weights, we have one weight for every feature, as we were doing with linear regression. So I just said, we have one weight for every feature. So the dimension of this would be 1 by features, okay? Then we get our data x. Okay, right now for this multiplication to be valid, we have to have our data like so. We have to have this dimension referring to features, okay? And the other dimension would be referring to samples, right?
Mm.
Okay, so what will happen if we multiply them again from linear algebra? We will just take this one, multiply it by this one, right? And we'll just loop and do that, okay? And the output should be, if we multiply them, the output should be 1 by samples, okay? But we are not doing this with the perceptron. We're not doing this with the perceptron. The perceptron has a unique property, okay? So it's used for classification, and it's used to update our weights with every sample, okay? So we can say that with the perceptron, there are updates with every sample, okay? And we can also say that we don't have very well defined cost, okay? We really depend on the weight update, okay? And the cost or the error itself is just something intuitive. We can calculate the error as the misclassification, okay? Okay, so if we have our data looking like that, to get the net input, to get the value of Z, what we would do, we would use just the first sample, okay, this one sample. So we would take this row multiplied by this column, and this will give us one value, right? Because when we multiply them, it's a dot product. So each element with the corresponding element, and then we add them together. So this would give us a scalar, right? So right now, Z will be a scalar, okay? And now what would happen when we use our unit step function? So we'd see if Z is here, then the value would be 1, okay? If it's on the other side, it will be -1. And from that, we will get our y hat, okay? And then after getting y hat, we would use our update function, our weight update function. So we will basically go to this equation and we will use y hat that we just predicted, compare it to the actual value of the sample, okay? Multiply this by x, multiply this by eta, and this would be our delta W. So again, let's think about dimensions. Z was just a scalar, one value. One value, it would be just projected here, it would be -1 or 1. So y hat will also be a scalar, okay? So let's use our function again, y hat minus y multiplied by x, and this will give us delta W. Okay, we know that eta is the learning rate, which is a scalar that we set to a small value. Let's say something like this. So it's just a scalar. Okay, and we know now that our y hat is also scalar. So y hat will be a scalar. Y is the true label of this specific sample. So it will be a scalar as well. So subtracting these will give us a scalar, and x is not a scalar. X is not a scalar, okay? Because we are updating this, as we said, with every sample, okay? So x is this column vector, is this column vector, okay? It has a dimension of features and 1, because it's just one sample. So if we multiply this scalar by this resultant scalar, we multiply this element by element, okay, with the features of this sample, we will get features by 1. Features by 1. This result is exactly our delta W. Okay, so this is our weight update. Okay. So what about delta B? Okay, the update of the bias. The update of the bias does not depend on the weight of the feature or the feature itself. So it's y hat minus y, and this is it, nothing else. Okay, so again, it will just take y hat, a scalar, minus a scalar, and eta is a scalar. So it will give us a scalar, and this would be our delta B. Okay, right now you have delta W, you have delta V. Go ahead and update your weights and keep calculating this difference and keep it changing your classifier up until the point you see that there is no difference between y hat and y. What would it mean if there is no difference between y hat and y among all samples? What do you think?
The classification is correct.
Yeah, the classification is perfect, right? Because y hat and y are always the same, right? So there is no difference between them. So this would mean that we achieved 100% accuracy, okay? And by doing this, we say that our classifier is converging, okay? We say that this is convergence. It's achieving convergence, okay? Okay, so any questions in this part?
Yeah.
Okay, perfect. So if you just notice, it's quite similar to what we are doing with linear regression. The objective itself is different, but the main idea, the main like take-home message is that you have a cost, whether it's a linear regression, whether it's a classification, it doesn't really matter. You really just have an error, and you see that this error depends on some variables, weight and bias, And you keep on optimizing the values of these weights and biases until you reach the minimum error. You reach what you want, whether it's a classification or fitting a line or something else. Okay, so it's basically an optimization problem. Okay, so let's try to go ahead and try to code this together. Okay, let's try to think about how we're going to implement this in Matlab and see if it's really easy or it's going to be challenging to do so. Okay. Okay, so I would just start with defining some things. So I would just get something from the linear regression, from our linear regression code. So we're just in the beginning defining some data and nothing else. So with this one, what I'm doing in this part, I'm just taking what we call a multivariate data because I wanted to have two features instead of just one feature. Because if you remember in linear regression, we had one feature and we wanted to predict the other feature. So yes, we had two features, but in this one, I would like to scatter the first class differently from the second class. So again, thinking about that, you would find it, I think, intuitive that in linear regression, we had just one scattered, let's say blob. This blob was like that, okay? But with classification, if we are going to simulate our data in linear regression, it will be just one blob like so, right? But with classification, we really need two of them. We need one for this class and another one for the other class. Okay. And that's exactly what I'm trying to do in the first part of my code. So what I was trying to do, I tried to take something that is called a multivariate Gaussian distribution. So a Gaussian distribution is a normal distribution. A normal distribution is scattered or distributed around the mean, okay? And it's distributed with respect to another variable, which is the standard deviation, okay? So from these sufficient statistics, from these mu and the standard deviation, we can come up with this nice normal distribution, this Gaussian distribution. And what I'm doing here, because this would be just 1D, one-dimensional, I need our data to be scattered into two dimensions. So what I'm using, instead of using univariate distribution, that's a univariate Gaussian, I am trying to use a multivariate Gaussian distribution. So basically, instead of thinking about this as a curve, think about this as a sphere, okay? Such that you would have a lot of samples in the middle, okay? And as you go away from that middle, you have less and less samples. And that's exactly what is happening. The middle is mu, and as we go far away from it, we have less samples. And here we would have a lot of samples and then less samples, okay? So this would result in giving us the data scattered like so around the mean. The mean is, of course, defined by mu1 and mu2. So we'd have a lot of samples in this region. And as we go far from it, we would have less samples. Don't worry if you really don't get what is multivariate Gaussian is doing. So it's just a way for me to simulate our data right now. And it will be really handy in the future if you would like to simulate data, because then you can just change some variables of this distribution to generate different data. Okay. Okay, so you would find in my code that I'm defining mu1 and mu2, okay, which is describing the center of the sphere, okay, and I'm also describing the covariance. The covariance is something different from the standard deviation that we're seeing here, because with the univariate Gaussian, we have variance and the standard deviation. The variance is explaining how far we are from the mean, how far we are from the mean. So if we are going here and there, we're so far from the mean. Okay. And when we have a huge distance from the mean, this would result in high variance. Okay. So what I'm doing in 2D is not just variance, it's covariance. Covariance describes the relationship between these two variables because we have two dimensions. So let's say we have x1 and x2. And then the covariance will describe how the data are rotated and scattered in this 2D space. Okay. Again, don't worry if this is not very clear. I'm just saying that this is handy in simulating the data and coming up with with this. And it's also, I think, handy in understanding variance and covariance and this kind of distributions as well. Okay, so this class will have its own mu1 and mu2. Okay, so let's go back to the code and see how this was done. So I was basically taking two mu's, mu1 um, for the first class, and then I was defining something called sigma. Let me zoom in so that it's clearer. Okay, so can you see the code now?
Yes.
Okay, so mu1 had two centers, okay, two centers, mu1 and mu2. Okay, here one is referring to the class. So these are the centers of the first class. So that's mu1, mu2. It's at this point, okay? And as I was saying, how this data is scattered and rotated and described by, this is described by the covariance, which is inside of this sigma matrix. Okay, and then I give this to a handy function in Matlab that will just generate our 2D points. So it will generate 100 points, and each point will be a sample. So each point will have two values. So we can assume that they are the height and the weight, as we were saying. Okay, and then I'm doing the same for mu2. I'm doing the same for the second class. Okay, so we can really say that this is for the second class. Okay, so okay, let's save this and call this perceptron. So this one for the second class, so I shifted the mean a little bit so that they are not really aligned on top of one another so that we can see the difference. Okay, and this is data 2. And here I'm just putting them underneath each other. So let's say that we stop here and we looked at our data, you would see that we have 100 samples, as I was saying, and we have two columns, we have two features. And data 2 also have 100 samples and two features, okay? And then here I'm aggregating them, so I'm putting them underneath each other, so it would have 200 by 2, okay? And then the labels, also 200, labeling them as the first 100 as 1 and then the second 100 as -1. Okay, so right now it's nice because we have our 2D data and we have our labels. Now we can really go into the actual code of the perceptron. Okay, so do you have any questions about like the generating the data?
No.
Okay, good. So here I'm using just one simple line, which is a random generator. So that's the generator seed. Okay, I'm fixing this to 2. And I'm doing this to be able to reproduce. It's something that we call a lot in machine learning, because you would like to really be able to reproduce your data, right? So if you just generate the weights randomly every time you run the code, you might run the code today, but if you run it tomorrow, the result will be different because the weights are initialized differently. Okay, so sometimes we like to generate our data or weights randomly, but we need to generate them randomly with the same numbers every time. So if you generate them today, they will be random, but they will be the same random numbers if you generate them tomorrow or next week. Okay. So here we are going to classification. Okay. So what we would do, we started by initializing our weights. So this would be a random number because we have 2 features. This would be a vector with this dimensions. It would be just 2 and 1 because it will have just 2 numbers. If we run this line, you would see now that it's 2 by 1. It has 2 rows and 1 column. Okay. And then we have our bias. So our bias will look like so. It will just be one value. Okay. And then we can start setting our parameters. So we have one parameter, eta, and we have another one, which is the epochs. Okay. So what is the epochs? Epochs is the iterations. Okay. So if we look at our gradient descent algorithm, when we started, let's say at this point, and then we kept trying to go to the global minima, this number right here of the number of steps that we are taking towards the global minima in order to achieve this, these are the number of epochs, okay? The iterations that we have over our data, okay? We call them epochs, okay? So we can initially have our epochs, let's say 200, okay? We'd have 200 epochs in our data. Okay, that's cool. So right now we can start training our perceptron, training our algorithm. Okay, so let's now think about the structure of this training. So if you remember in linear regression, we were having this epochs or iterations, and we were just looping inside these iterations and updating our weights. So we had only one loop, one for loop, okay? So right now, let's look at our explanation here and think about the structure of the perceptron algorithm. So do you think we would have one for loop or 2 or 3? What do you think?
This one. 1.
1. So we have one for epochs, okay? That is correct, that we have one for epochs. But the thing is, we said in the perceptron that we will be updating our data with every sample, right? So this weight update will be changing with every sample. So after this sample, we'll have delta W and we'll change the weight. And then we will go again and take this weight multiplied by the next sample, right? And we'll get delta W. And the next one will get delta W. Okay. So with the change W, as long as we are looping on the samples. So we would need another loop, okay, on the samples. So if we really think about just projecting this like explanation on the code, it would be a loop for the epochs, and inside of this epoch, each one of them will contain another loop on the samples, right?
Yeah.
Okay, perfect. So let's now convert this thought into code. Let's try to think about it. So we'd have a loop. This loop will be looping on the epochs, right? So this will go from I equals 1, okay? And this will terminate at the epochs. And this is our first loop. And inside of this one, we will have another iterator that would loop on the size of our data. So it will have the length of labels, okay? Because the labels is the has 200 element, which is the number of our samples. So I'm just getting the length of that. So here we would loop on the samples. So that's the main structure, okay? Okay, so inside of this, what would happen? So firstly, we need one sample, right? We need the first column of our data. We need this first sample right here. So I would just take X to be data of J, because that's the iterator on the samples, and all, because the data is 2D like that. I'm just getting J and all. So the first sample and all, okay? So by doing that, we get our first sample, and we have our label J, because that's the current label of the sample. Now we can go ahead and just do our calculation for the net input. Okay, so the net input Z is calculated by doing what? By multiplying the weights by X and then summing the bias, right? So that's exactly what we are going to do. So we just do this multiplication of the weight with the first sample. Okay, let's do this. So we'd have our Y predict, okay, which would equal Y transpose X. As we were just explaining, we would take W transpose X, okay, and then we would sum the bias. Okay, now we can apply our unit step function. Now that we have multiplied the weight transpose by X, we have Z. Now we need to project this Z on the unit step function, right? So we need to say if this value is higher than 0, then it will be 1. If it's lower than 0, then it will be -1. Okay. That's exactly what I'm going to do here. So I'm taking Y predict and I'm saying Y predict higher than 0. If this is higher than 0, I'm going to set it to 1. Here I'm not doing a condition. You can do this with a condition. I'm just doing this like so, because if it's Y predict of Y predict higher than 0, then if it's positive, then it will be 1, and then this will be uh, 1. Okay. And then Y predict lower than, let's say, or equal 0, this will give us -1. Okay. And then the weight update. So right now we have just taken our value X. We have W transpose X. We have our net input function. We have applied the unit step function in these lines. We need to update our weight. So right now W equals W minus delta W. Delta W is eta. I'm just putting in the equations, nothing more. So eta y hat minus yx. Okay, so this would be eta y hat minus y. Our y hat is y predict. Okay, minus y. Okay, and we'll multiply this by x. Okay, and the bias, the update of the bias is the same without x. Okay, so that's why I removed x, and this would be bias. Okay, do you have any questions in this part?
Mhm.
Okay. So if we loop inside of this loop, it should be updating the values of W and B such that it really minimizes this error. Okay. And we can iterate until we exhaust or we finish the number of epochs. Okay. Or we can terminate. So we can here see the total error, and then we can terminate here if we find that our error is very low. Okay. Meaning that we sum the error that we got in this part and we count how many of them are correct, how many got y predict equals y, and then we get this error. And then we have a condition here. We can put a condition here. If we find zero error, so no misclassification, then we can break from the loop. Is this clear?
Yeah.
Okay, perfect. So how about visualizing this? So let's assume that right now we need to visualize our decision boundary, the line that is separating our data. Okay, so we would say that this is our boundary. Okay, but let's for doing our classification, let's test our classifier. Okay, right now we need to know if our weights and biases are really good or not. Okay, so we really need to test our classifier here. So let's use the same data to test the classifier. So I'm just projecting the same data and seeing whether there will be any misclassification. Okay, so I'm going to use y predict to get the weight. Okay, right now the weight, of course, after the loop will be the final weight, so it will be the optimal weight. Okay, so that's the good weight and at the end. Okay, and right now I need to project the same data, so I'm seeing how good is the classifier with the same data, because the thing is, a classifier may be not very good at the same data. So let's say that we have data looking like that. Okay, the classifier might not be a perfect classifier, okay, because it's still a linear classifier, meaning that it needs to draw a line. And there is no line that you can draw, okay, that would separate this value from these, okay? So perhaps the best line would be this line, the drawn line here, okay? And even with this line that we draw here, we can see that the classification would have this value as error, correct? So let's say if we have 100 samples and we project the same data on this classifier, this model, that would have 99%, okay? Because this would be a misclassification, okay?
Yeah.
Okay, perfect. So going back to the code, I'm just trying to project my data again on the same using the weights. Okay, so we'd have data and then plus bias, because now we have our original data. I'm gonna just multiply this with the final weights and final bias that we got. Okay, that would be y predict, and then we know that this W transpose X plus bias is the net input, so this would give us Z. But Z is now continuous, so we need to make this binary. We need to convert this into -1 and 1. So here, if you look at this line, it's just very similar to this one, because that what we were doing. We're just projecting the data with the new weights and bias. But the only difference is here that we're using weights and bias from the final iteration. And in this part, I would just copy paste this because it's exactly the same. I would just have a unit step to binarize our y predict value into 1 and -1. And the reason I'm doing this is that I'm gonna compare this now to our true label. Okay, so what I'm doing here, I'm comparing labels, which is the true label. Okay, I'm comparing this to Y predict, because Y predict is now containing the predictions from the classifier, and we are comparing them to labels. And here I'm saying if they are equal, this will give us 1. So here I'm just summing the values of ones, okay, and dividing them. I will divide this by the length of labels, okay? So when we divide this by the length of labels, this will give us um, the accuracy, okay? And we can multiply this by 100, okay? Because here I'm just counting how many of them are correct and then dividing by the total length, okay? The total number of samples. So that's accuracy. So we can say that this is accuracy, okay? Okay, so let's try to run this and see if there are any errors or something, and then we can see if there is high classification in our data. Okay, so looking at that, we have a mistake somewhere. Yes, so we got this data to be one row vector actually, and we should be transposing this because W transpose is now row vector. Okay, so X should be one column. It should be column. So that's why I'm doing this transpose. So let's see if this works. Okay, perfect. So now it's working and it's giving us the final values for weights and the buys as well. Okay, so let's test our data. So now I'm projecting the same data. I'm trying to look at the accuracy. How many of them are correct? Okay, and we can see the accuracy is really poor. Okay, with this one. So we can't just visualize the boundary. So let's try to visualize the boundary to be able to visualize this. So we would scatter our data. Our data 1, okay, because we have two data sets. I'm just trying to isolate the first one from the second one. So we'd have data 1 showing the first feature and then the second feature. Here is something just for visualization, so don't worry about it, okay? And then we'll scatter our next data. And this would be R. Okay. And then we can do something slightly different. So here I'm trying to test my classifier with different data. So I will try to tell you what I'm doing in this part because it's important, I think. So right now we know that we can get any value, right? And we can just know if this is classified under the line or above the line, correct? So what I'm trying to do with this one, I'm trying to actually visualize this boundary, visualize this line, okay? So I need, first of all, I need the equation of this line, okay, to be able to visualize it. And I need different points on the x-axis such that we can plot the line. Okay, we can plot the line. We have to have many values on the x-axis and then project them with the equation to be able to draw the line. Okay, so with the linear spacing part, I'm just taking values from -5 to 10, and I'm taking 100 value. That's what I'm doing at this line. Okay, such that we can take all of these values and substitute in the equation and draw this line. Okay. Okay, so what about the line itself? How to get the equation of that line? Do you have any idea or suggestion? Try
No.
to think about it. It's okay if you can't figure it out because it's not
Yeah.
very easy. Okay, but try to think about something that we had our net input looking like that. We had first weight multiplied by the first feature and second weight, second feature, like so. Okay, and then we had the bias, correct? And this was implicit because that was W transpose X. But this is really what is happening inside. The first weight with the first feature is multiplied by the first feature and so on with the second feature as well. Okay. So we used this value, we projected in the unit step and we get our Y. Okay. So our Y is really coming from using the first weight. Okay. And the bias as well. Okay, so right now let's think about it. We named our classes, we labeled them -1 and 1, correct?
Yeah.
These were the true labels of our classes. So right now the boundary, let's say intuitively, without any calculations, intuitively, our boundary is something in the middle, right? It's not something that belongs to either of the classes. So if this class is -1 and this class is 1, our boundary should be at exactly 0, right?
Yeah.
Okay, so that's nice because right now we have an equation for this that describes this value of y, this value of anything that we are showing here. So right now we know that our value could be -1 and 1, but for the boundary, this value should be 0, right? So it will be W1 x1 plus W2 x2 plus the bias, correct?
Yeah.
So from this one, we already got the weights. It's good. So we have exact values for the weights and we have exact values for x as well. So that's good. Okay. So right now we need to draw the line. We need to draw this line. So we need to substitute with these values. So these are on the x-axis. So that's x1 and this is x2, the y-axis. Okay. The first feature and the second feature. Okay. So right now I got some values for x1 in this line, the linear spacing. Okay. I need the equation of the line to substitute these values and get x2. And that's how we will get the line. Okay. So we need to get x2. Okay. So what we can do is basically solve this equation. Okay. So what we can do is looking at this equation, we would say that we need to calculate x2, right? Because we already got from the function of linear spacing, we get different values from x1. So we need just to substitute in this equation and get x2. So we would say that in order to get x2, it would be equal to, let's put this to the other side and this one to the other side. So it would be minus w1 x1 minus bias divided by what? Hmm.
0.
So no, we get this we put it to the other side, we put this one to the other side, okay? And then this would equal to W2 x2, right? I'm just
Yeah.
putting them to the other side. And then I will divide by W2 just to get x2,
Yeah.
right? Okay, so it will be W2. And this would be our equation for getting the values of x2. And these will be the points that will plot our line, our separating line. Okay. So let's go to the code, and I'm just gonna code this simple equation right here. Okay, nothing more. I'm gonna name x2. I'm gonna name it y value because it's on the y axis. So we would have our y val equals minus b Okay, that's the bias, minus W, the weight 1, the first weight, okay? And then this would be multiplied by X, and then divided by 2, okay? And then we would plot this. So we'd plot X, we'd plot Y val, and let's give them nice labels. So we'd have X label, this would be feature 1, and Y label would be feature 2, and yeah, I think that's enough. Okay. Okay, so before doing that, I think we have almost finished the perceptron, and we have seen how to look at the boundary. And back at the code, there is a very tiny typo that we had in the first code actually, which is at this line. So it's funny because we started this array should be equals 1 and then goes to the length. And that's why it was giving us 52% accuracy. Other than that, if we run this code, it gives us 100% accuracy, and it runs just fine, and we can see that classifies all of our samples. Okay, so now we can move to another algorithm, which is the Adaline. The Adaline is another linear classifier that is used in machine learning. And before going to this, we could take some notes about the perceptron and really think about the perceptron. So in the perceptron algorithm, what would happen if we center our data or we do not center our data? So there is something very important to note in doing such a classification. If we have our data looking like that, so we have two features, we have x1 and x2, we have different samples. We can take the average of this, okay, and this would be mu1, and we can take the average of that, and this would be mu2, okay? And if we loop on our data and we subtract this mu1 from each sample, then we would guarantee that our data will be centered, meaning that this data will have mu1 equals 0. And I will show you visually how this is done. And the same thing for mu2, if we loop on this and we subtract mu2 from each one of them, we would guarantee that we are centering mu2 to be 0, okay? Then what will happen if we divide this by the standard deviation, of the data? The standard deviation is explaining how far we are from the mean. So let's say for one sample X, if we have, let's say, X1, X2, X3, X4, explaining different samples like so, okay? Let's put them between these brackets. So if we took the average of them, if we took their average, this would be X bar or mu1, and then we can divide this by the standard deviation. We can divide this by the standard deviation. This would guarantee that the mu will be 0 for all of them, and the standard deviation, by dividing this by the standard deviation, this would guarantee that the data is scattered and have a standard deviation equals 1. Okay, I will show you how this is done and why this is done, and what will happen if we don't center our data, basically. Okay, so by doing that, we would, if we look at the standard deviation, so let's look at the standard deviation alone. and see what the standard deviation is doing. So the standard deviation is coming from the name actually. So it's looking at how much we are deviating from the mean. So if we have our data really scattered around a specific point, which is the mean, the standard deviation, which is the square root of the variance, is explaining how far we are from the mean. If we are very far from the mean, we would have high variance and high standard deviation. If we are very close to the mean, we would almost have zero variance and zero standard deviation. Okay, so how much we are deviating from the mean. Okay, so it's also explained by x minus mu. Okay, and we just normalize this. Okay, we just normalize this quantity. So how far we are from the mean. Okay, so let's look at the data. Let's look at our data and the example that we had. The data were scattered around here. So let's say that we had our data like so. So we really had an average mu1, an average mu2 for the first and second feature respectively. Okay, so centering by the way is this part. We call just this part, we call this centering. Okay, and if we divide this by the standard deviation, we call all of this. So if we do centering and division by standard deviation, we call this standardization. Okay. Okay. So we really need to standardize our data for the machine learning algorithm before doing our calculations. Okay. This is not always the case. So for some models, they can handle the data even if they are not standardized. But it's really nice to have them standardized in general, just to be sure that the data is scattered in a good way for the classifier. Okay, so the reason that we are doing this standardization, if we looked at this, we really are trying to bring our data. If we just subtract mu1 and mu2, what will happen to this data? This would become the origin, right? Because you are subtracting mu1 and mu2 from all of these data, right? So we are bringing this to the origin and you are bringing this to the origin. Centering would be really nice to bring your data to the origin, okay, and make sure that the standard deviation is 1. The data is scattered around the standard deviation of 1, okay. So why this is important? So let's look at the cost-weight relationship to see why this is good and important actually. So if we looked at our relationship between the weight and the cost, and we said that if we have two weights, let's say W1 and W2, or weight and bias, we said that it can be represented in 3D shape, right? And we said that what is inside of here can be expressed as the global minima, okay? Because the shape was just a curve in 2D, but then it would be in 3D explained by this. So this part would have high cost, and as you go towards this point, you are minimizing the cost. So when you change W and W2, you are going towards this global minimum. Okay, so the issue is that if you don't have your data centered or standardized, your data would have this shape. So it would be almost like a sphere. Okay. And the issue is that if you initialize your W1 and W2 and you begin your journey from this point, and then you try to go to the minima, you would have a high distance, you would have a big distance from the global minimum. And if you start your data randomly from here, you would have a different distance to the minimum. Okay, so it looks like this is not a symmetric shape. You don't guarantee that if you start from here or from there, you would reach the global minima in the same steps. Okay, so what we really need to know is whether we can have our data and our shape to be symmetric like this of the coast, okay, of W1 and W2. And that is what standardization is doing, okay? Because when you standardize your features like so, the features now, even if you have a high numerical value, so let's say that our features x1 and x2, one of them is like 100, 101, 104, and so on. And the other one is just 0.1, 0.2, 0.3. There is an issue because the scaling of the first feature is different from the scaling of the second feature. Okay. And this will make the boost weight relationship look like this. Okay. So it could give one of the weights high value. Okay. And the other weight, it can give it a low value. Okay. For the weight. So this weight could be low, okay, and this the weight of this one could be high. So we don't want to do this. We don't want the scaling of the features, this scaling factor, to change how we do our optimization. And that's why we do standardization. By doing standardization, this will bring this point to like 1, 0, 1, and this one to 1, 2, 2.5. You would notice that the values are now around 0 and 1. All of them are small values. It will be 0 0.1, 0 0.2, something like this. Okay. And by doing that, this will make the shape of the cost to weight relationship symmetric like so, such that when you initialize your weight at this point and you go ahead and optimize your weights to get the lowest cost, to get to the global minima, you would guarantee that the number of steps you take are equal to the number of steps you take if you initialized your weight from this point when you initialized your weight from this point. And you would guarantee that none of the weights, none of the features is scaled differently from the other one and controls how the weight is being updated. Okay. So it's really nice to have your weights standardized in this manner. Okay. Any questions in this part?
No.
Okay, perfect. So going to the perceptron again, there is a very important parallel between the perceptron that we are seeing, okay, and the human brain. And that's why they are coming up with the names and saying that this is an artificial neural network and things like that, okay. So the human brain contains, on average, around 86 billion neurons. It's a huge number. Okay. Those neurons are having an activity. So a neuron would look like this. So a neuron would have a shape that looks like that. Okay. And then we have a connection here. This would be an actual neuron. Okay. And here we have something called the sheath. And here we have terminals. We have axon. Okay. And we have these connections are called dendrites. Okay. Okay. And these connections are actually connected to another cell, another neuron. Okay. So there are so many of them, and all of them are interconnected like so. Okay. So here we will have another one, and here it's connected to another one, and so on. Okay. All of them are constructing what we call a neural network. okay? And the average of this neuron, the length of this neuron would be 1 millimeter. That's very small, okay? This neuron has an activity, has electrical activity. This neuron can do something that is called firing activity, okay? Firing. We say that the neuron is firing if it's producing an activity, okay? So it's like logical one. There is an electrical activity, okay? So this is a nice parallel to what we are trying to say here. It's not perfect. So what we are looking at with our artificial neurons is actually different from this neural network a little bit. But this was the main motivation why we have the perceptron and the neural network. So let's look at the architecture of the perceptron. Okay. So we say that this is an architecture, and this is a terminology that we'll use a lot. Okay. Architecture. Architecture is basically how the nodes or the points are interconnected together. So we have features, we have x1, x2, and so on until xm. We have features, and those features are weighted. So each one of them has a weight, each one of them multiplied with a weight, and then we sum all of them. And that's how we get our net input function, z, okay? And then we do our unit step function, which looks like that. And then we get our y hat, the predicted value. Okay, so this is the architecture of the perceptron. Okay, with the actual neuron, it's just firing or not. Okay, but this was a motivation to create the weight, for the neurons. Okay, and really think about the weights that are multiplied by the feature and then added together, because these neurons are then aggregated together in another neuron. So let's say all of them are connected and there are, let's say 100 in this part, then this neuron, if it's connected to a lot of them, it's like adding the firing effect or the effect from other neurons as well. Okay, so they are added together, and then whether there will be an activity from the population of neurons firing together or not, this would be something at the end. So this was a motivation for us to work on something like the perceptron algorithm. Okay. And by the way, why we are calling this and how this relates to the neural network as a name, because this is still a classifier, this is still a single neuron. We call this node. Okay. This whole classifier, this whole architecture, we call this a node. Okay. A node like this, empty node like this. Okay. And then we can connect several nodes. So we can have several classifiers taking the values of the features, okay, taking all of them, taking the values of all features, okay, like so, and then we can connect this to another node. So basically many classifiers connected together, okay, and we call this NN, neural network. Or ANN, artificial neural network. Okay, so any questions in this part?
No.
Okay, perfect. So this was more of like the motivation for why we are doing this, in this particular way. Okay, so now we can go to something else, which is the other line. The other line is the second algorithm that we will talk about today. It stands for adaptive linear neuron. Okay, adaptive linear neuron. Okay. We say that in other line, we would have a cost function. We have a cost function. we have something else. We have something that is called the activation function. Activation function, which is actually very handy and very important to introduce some nonlinearity to our data, but in Adaline, it's linear. Okay, so the Adaline algorithm works as follows. So we take our cost function, which is actually the same one that we used in linear regression. Okay, summation from I equals 1 to m. And then we take y hat of I minus y, and we square this. Okay, so this was our cost function. So the thing is, now we would differentiate this with respect to w. So it's going to give us the same update that we used before. I equals 1 to m. Okay. Multiplied by x. And we put here our learning rate eta. And we differentiate this with respect to the bias. It's going to give us, of course, eta. Okay. Y hat minus y. Okay. And the difference between the Adaline and the perceptron is that, first of all, we have a cost function. Okay. And the second thing is we have an activation function. And there is also another difference that we have our model working on all samples. Okay. Or we could say uses all samples. So it's using all samples together. So it really uses all samples at once. Okay. And by the way, when we refer to using all samples at once, like using the whole training set, we call this batch. So we are saying that we're using the whole batch that we have. Okay. So that's nice. So we have a cost function. We have our update. We can just work on our model, right? So if we think about the activation function, because that's now the thing that we still didn't know, okay, we would say that for the other line, we start with the weight. So that's W transpose, and then X. So this would be 1 by features. As we said before, this would be features by samples. Right now, in the other line, we are acting on all samples. So instead of updating the weight on after each sample, as we were doing in the perceptron, we are updating the weight after the whole batch, okay? When we loop on the whole batch, okay? So we will multiply this by this, and this again by this, and so on. And then we would have our net input. Z equals W transpose X, okay? And this would be 1 by samples, okay? And this right now 1 by samples, and then we will use our activation. Before we were using a unit step function to just see the label. Here we are using an activation function. The activation function of the Adaline is linear, meaning that we take Z, we map this value of Z to something else, phi of Z, okay? But this is linear, this is not changing. So the value of Z will actually equal the value of phi of Z, okay? All the time. So it's like almost not doing anything. It's not almost, it's really not doing anything, okay? But the activation function in general will be very important in something like logistic regression or something else, okay? So the main concept is that you are introducing some changes to your data. You are mapping Z to something else like 5Z, okay? So we could use some other function, but this is not Adaline. That's just a thought on using this activation function. We can use something not linear. We can use something like this, okay? And this function is called the sigmoid. And this is actually the activation function for the logistic regression classifier, okay? This will take the value of z, map it to the value of 5z, introducing this nonlinearity, okay? So we take the value of z and see the corresponding value of 5z. Okay, and 5z of course has its own equation that we would see, such that we put any value for z, substitute in the equation, and take the corresponding value of 5z. Okay, okay, so back to the Adaline. We get our activation function. We know that mapping z to 5z will still result in the same dimensions. So we'd have 1 samples. Okay, and this would be our y hat. This would be our predicted values. Okay, then we can compare this to y, which is also of the same dimensions, 1 by samples. Okay, and when we take the difference will be 1 by samples, and then we take that difference, we multiply it by x to get the update. Okay, and for that we put our x data into these dimensions, samples by features. We put it like so because we need to multiply this result that we just see, 1 by samples, okay, by x. So I would just take this, I would name this difference, okay. I put this difference here. We could name this error as well. Okay, so this is 1 by samples multiplied by x. That's why I put x as samples by features to be able to multiply them. So this would be 1 by samples multiplied by samples by features. So this would give us what? So what would be the output of this multiplication? It should be 1 by features. Okay. And that's good because 1 by features is the update. So there is an update for every feature. Okay. So this would give us delta W, the update. Okay. And if we do the same for the bias, we would get the update value for the bias, but we're not multiplying by anything. Okay. We're not multiplying anything. We're just getting y hat minus y, and then we're taking the average of that, and that would be delta b. So it will be just one value, a scalar. Okay. So any questions in the equations or like in this diagram that we could use to implement our Adaline algorithm? Okay, is everything clear?
Yeah.
Okay, perfect. So let's go and try to see the Adaline algorithm. The Adaline algorithm is slightly different, and we could think about just, let's say that we would actually take the same code, okay, and just change this code. I would just change this code. Yes, let's think about this together. Okay, so the same way we generated the data, we would just use exactly the same method, okay? And then we just think about how we would do or variate this to become the other line. So let's think about it. Let's bring the slide and think about this. In the perceptron, we had two loops because we were looping on samples, correct? Do you think that we would have one loop or two loops in the other line?
One.
Yes, we would have one loop because here we just have the loop of the epochs. We don't have to loop over samples because here we are acting on all samples at once. Okay, so if we looked at this, like we look at the dimensions together of the data to see what is going on here, we would remove this loop. We would just have our data that we will use to multiply with. So we'd get rid of this loop, okay? And our data will be with this dimension. So let's think about it. So we have samples by features, okay? So we can get rid of this because now we need the whole data at once and this as well. So our y will be labeled, so we can bring this outside of the loop, okay? Because now we are not dependent on the loop, so we can bring it outside the loop. Okay, now let's think about it. So we have our weights. We have our weights looking like that. So W transpose will be row vector. And then we have our X values like so, and then the Y's. Okay, this looks good. So we can get our Y predict. It will be a huge row vector. And this is exactly correct because if we look at the dimensions, when we multiply this by this, we would have 1 by samples row vector. So this would be our Y predict or the Z value for now. Okay. And then we need our activation function. Okay. We need to map Z to phi of Z. These were the lines for the unit step function. We don't have a unit step function, so let's remove them. Okay. But we have phi of Z. So let's say that we have phi Z, okay, which actually the same as Z because we are not doing anything else in this part. The function is linear. It's just taking this and mapping it to the same value. So phi of Z will be the result of y predicted will be the same, okay, and then we can take phi of Z. Now the weight update, we get our y hat will be y hat minus y. So y hat minus y, multiply this by eta, multiply this by eta, and then by x, the same update. So we take 5z minus y. So let's look at this. So 5z will be 1 by samples. And this would be like so. So let's do it like that. So y hat minus y will be 1 by samples. So we need to transpose our data to handle this. Okay. And our W will now update. But the thing is, we need to transpose this. So let's think about it. Eta is a scalar. Phi Z is now a row vector, 1 by 200. Our labels is 200 by 1. So the size of this one, let's look at the size of this quantity right here. It will be 1 by 200. We multiply this by 200 and 2. So it gives us our weight update, but our weight update was actually a column, so we would need to transpose this value after doing that. Okay, here I'm just fixing the dimensions, and that's really the thing I would need you to think about when you are doing such coding. So look at the concept, really understand the concept, and try to take a paper and just draw the dimensions and know when the multiplication is valid and when it is not valid, and you need to change or transpose something. Okay, so here I was transposing this in that way. Perhaps we can do it in another way and it would still be valid. Okay, so let's actually try to brainstorm a little bit about this. So if we don't do it in this way, what will happen? We have 5z looking like that. Perhaps we could transpose this such that it becomes a column, and this is now valid because that's a column and the other one is also a column. We would need to take the difference. It would be a column as well. So perhaps we could transpose this such that it becomes a row, and then we multiply this by x. Let's look at the size of that. It's 1 by 2. So what I need to do right now is, because our w is a column, so we need to make this a column as well. So let's run this again. So the result of this should be a column right now. And this is correct. And now our w is updated. 5z is a row, and this is a column. So we change them. And here we actually need to normalize as well. So from the equation, looking at this equation, we are summing, okay? And then we are dividing by m, okay? So we need to divide by m. So after doing that, we need to divide all of this by the length of our samples with labels, okay? And in the other one, we have 5z minus y. And here I'm just matching them to be equal. So that's 5z, that's row, okay? And the other one is transposed, so it should be row as well. Okay, good. And then we can, so of course it could be difficult to just trace everything with me right now, that I will send you the recording of that such that you can code this yourself and trace it on your own, or just look at the video and trace it with me and the recording. It will be easier. Okay. And then I'm just trying to make this of equal dimensions, so they will be, this will be a row, and then we can then apply this part of the equation. So we are summing and then taking 1 over m, such that we are just taking the average. So here we can take the average. So take the mean. Okay. And that would be our output for that. Okay. And we can then see what will happen with our data. So I have run this part such that we have WMB. Okay. We finished the number of epochs, 200. And you can see, if we look at this, I'm just projecting the data in the same way I was doing with the perceptron. We can see our accuracy. Okay, if we run this, our accuracy is 100%. So that's really good. So this classifier was able to classify all the data points. And I've now visualized this. So if we look at the figure, you would see this very nice decision boundary separating them. And you would also notice that this decision boundary is actually coming exactly in the middle, because that's actually a nice property that is not really biased towards any of them and just classifying them anyway. No, it's actually classifying them and making sure that this decision boundary comes a little bit in the middle, because that's something actually a little bit intrinsic in the algorithm, because it's always taking 5z, which is a continuous variable, and trying to make this as close as possible to the actual label, to the actual value of that label. So even though we have our classifier classifying at 100%, it wouldn't have error to be 0. Why? Because the error is defined as 5z here and how it differs from the actual label. And 5z is continuous. It's a continuous value, right? Coming from multiplying w and x and then adding b. So it's a continuous value. We don't have a unit step that binarize this value. So it's still continuous. So when you take the difference of that and y, there would still be a difference. Okay, and that's why there would still be an error. And of course, we can just calculate this error. So we can calculate this error the same way we did for linear regression. So we can use the equation that we just wrote. Okay, we can say that the error of I would just equal the mean as a sum squared error. So we take the mean, we take half of that, exactly like we did with linear regression, y hat minus y. So basically this, y hat minus y, okay? And then we square that, and this would be our error, okay? So we can actually do something nice. Let's try to visualize the error such that I have an error with every epoch, and here I would try to visualize the error. So I would just plot from 1 to I on the x-axis. So just the iterations that we have and the error value that we would have from that, okay? Okay, so we can nicely see that in the beginning, in the starting iterations, on the x-axis we have iterations. So in the beginning, we had very huge value for error. And as we go with the iterations, we then had very small value for the error, okay? And if we checked the final value for the error, or let's say min of error, which is the minimum of the error, it's almost 0. It is not exactly 0, okay? Okay, so this is it, I think. So that was the perceptron, and the other one was the line, and we have coded both of them, and they are actually the core concepts for more sophisticated algorithms, and they are the basic building blocks because these are the nodes that can be put inside of an artificial neural network, and we can then play around with the activation function to have a more sophisticated uh, model that can classify something that is harder to classify with these models. However, these models are really good to know what they are doing because these are the main nodes. These are the main things. Okay, and just by varying the activation function, as we are saying, we can get some interesting things out of our data. Okay. Thank you so much for seeing this video, and I would be happy to have you in the upcoming ones when we talk about more advanced algorithms in machine and deep learning models. Thank you.